Hello, my name is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar, What's New in SigmaXL version 9. Part 2 of 3, Time Series Forecasting. And the webinar will be approximately 45 minutes long, and then we'll have 15 minutes for question and answer. And I request that you would type in your questions. You can type them in during the session, but I won't get to them until the end, and then I'll read the questions out and answer them. Also, the webinar is being recorded and will be available for viewing in a couple of weeks after the webinar. PowerPoint slides, the data sets, and the workbook are all available. The workbook and the data sets come with SigmaXL version 9, and the PowerPoint will be available for download after the webinar. So with that, we'll start. We'll look at our agenda. We'll start with an introduction to time series forecasting. I'm going to keep it on the light side, not get into a lot of heavy math, just the essentials. We'll talk about autocorrelation. We'll give an example, chemical process concentration. We'll talk about simple or single exponential smoothing, information criteria, forecast accuracy, monthly airline passengers example. That's the famous data set from Box-Jenkins. Seasonal data, and we'll look at seasonal trend decomposition plots, spectral density plots, error trend seasonal exponential smoothing models, and we'll look at ARIMA, AutoRegressive integrated moving average models, and just briefly touch on partial autocorrelation, ARIMA with predictors, and then we'll look at a third example that uses electricity demand with temperature and workday as predictors, and then questions. So let's see, first of all, okay, so introduction. A time series is a series of data points indexed, listed, or graphed in time order. Most commonly, a time series is a sequence taken at successive equally spaced points in time. Time series analysis comprises methods for analyzing time series data in order to extract meaningful statistics and other characteristics of the data. Time series forecasting is the use of a model to predict future values based on previously observed values. So just a couple of points that I want to bring out here. There are certain situations that are good for time series forecasting and others where they will be of limited value or of limited use. So examples where time series is particularly useful include things like electricity demand, where it's well known that electricity fluctuates, the demand is going to fluctuate with temperature, time of the day of the week, and whether it's a holiday or not. And so we can put all of that together and build a very powerful predictive model. Same with retail sales, demand forecasting. Those types of things are really suitable for time series forecasting. Analyzing data to predict a stock price is probably far less useful because of the volatility. Things change and they change rapidly, and the past history is not a good predictor of the future. And so while people do use time series forecasting in financial markets, it's not particularly, in my opinion, all that useful. So the examples and the area we'll be focused on are the more classical applications such as demand and retail sales, that sort of thing. The tools that SigmaXL provides include a run chart. These are the new tools in SigmaXL version 9. Run chart, autocorrelation function plot, we'll talk more about that in a moment, partial autocorrelation plots, cross correlation, seasonal trend decomposition, and spectral density plot. Now, of these, we're going to cover all of these except for the cross correlation plot. So I would just recommend, if there's anything that I don't cover in this webinar, just refer to the workbook, and we have detailed tutorials and explanations on the tools. Just for the time limitation, we can't cover everything today. Also, for methods for time series analysis and forecasting include exponential smoothing with multiple seasonal decomposition. So sometimes you have situations where you not only have monthly data, but maybe you have a monthly effect, but you also have a daily effect or a weekly effect. And that's called multiple seasonality. And that's another area we won't be looking at today. It's a more advanced topic, but just to mention that we do have tools to handle that type of data. ARIMA, Box-Jenkins, AutoRegressive integrated moving average, ARIMA with predictors, and ARIMA multiple seasonal decomposition. So just some guidelines. There's a lot of tools here. So just to give you kind of a guideline, first of all, should I use exponential smoothing or should I use ARIMA? Really, they're two different approaches to forecasting, and you can really use both and take an average of the two. That actually works quite well. If you have negative autocorrelation, ARIMA is recommended. If you have predictors, then you have to use ARIMA with predictors. And if the data are seasonal, you have to specify the seasonal frequency. Note, frequency is the number of observations per cycle unit of time. So monthly sales would be seasonal frequency of 12. That's 12 months per year. Quarterly revenue would be specified as seasonal frequency equals 4. Hourly data would be 24. So this is a little bit different from the physics or electrical engineering definition of frequency. It's more frequency as used in time series forecasting. Exponential smoothing is limited to a maximum seasonal frequency of 24. So if you have a higher frequency, let's say you're looking at weekly with a seasonal frequency of 52, then you would want to use multiple seasonal decomposition, and that can accommodate higher frequencies. And what happens in MSD is the seasonal component is removed through decomposition. A non-seasonal exponential smoothing model is fitted to the remainder, including the trend, and then the seasonal component is added back in. So that's how forecasting is done with multiple seasonal decomposition. And multiple seasonal decomposition also accommodates multiple seasonality. ARIMA does not have a theoretical frequency limit, but we recommend that if you have a frequency greater than 52, to use the multiple seasonal decomposition. Note, ARIMA with predictors, multiple seasonal decomposition is not available. Some other notes: ARIMA assumes that the time series is stationary. That is, the mean, variance, and autocorrelation structure do not change over time. And if that is not the case, then corrections will need place. So, for example, if the mean is not stationary, you can correct for that by differencing, computing the difference between consecutive observations or between consecutive periods for seasonal data. So January of 2019 minus January 2018 would be an example. If the variance changes over time, then a Box-Cox transformation can be used, and we'll be demonstrating that in this presentation. Exponential smoothing does not require stationarity, so that's it's more flexible than ARIMA in that way. Both are useful. You can try one, try the other, and look at the statistics, look at the prediction errors, and see which model gives you the better. If you have a theoretical reason for using one over the other, then obviously you would make your selection that way. But practically, they both work well, and a lot of it just depends on the data, depends on how much data you have. And so I would just recommend trying both and see which one gives the better model. And the other option is to take the average of the two, and that actually works quite well. This is the forecasting menu. I'll, of course, be demonstrating that in a moment. So you have your run chart, your ACF plots, your cross correlation plots, seasonal trend decomposition, spectral density, exponential smoothing forecast, and the control chart. The control chart we're going to cover in the next webinar in December. And then the ARIMA forecast, ARIMA control chart, and there are some utilities that we include as well. So to start, I want to start with talking about autocorrelation. And basically, just as correlation measures the extent of a linear relationship between two variables, autocorrelation measures the linear relationship between lag values of data. A plot of the data versus the same data will show a positive or negative trend. If the slope is positive at lag 1 or lag 2, the autocorrelation is positive. If there's a negative slope, it is negative autocorrelation. And here's the formula. Again, we're not going to get into the formula details, but if I was to take some data, this is the actual chemical concentration data that we'll be looking at, and I was to shift the data, lag at 1, and then apply a correlation plot, correlation matrix to this data, each of these produces a correlation coefficient. And then what we do is the ACF plot, each of these bars corresponds to correlation for lag 1, lag 2, lag 3, lag 4. And if the correlation exceeds the significance limit, then we conclude that we have significant autocorrelation. First example we're going to use is the chemical process concentration run chart, chemical process concentration data, or Series A from Box-Jenkins. And we'll start with the manual example for exponential smoothing, and then we'll use SigmaXL to create the model. So exponential smoothing, this is the simple exponential smoothing forecast. It's a smoothing function, and what happens is that as the data gets older, the weights get smaller. So alpha is the smoothing parameter. This is also known as the exponentially weighted moving average. And visually you can see, for example, if I have an alpha of 0.2, then the data, the weights drop off gradually. If I have an alpha of 0.8, the weights drop off very quickly. And depending on the alpha value will determine your best predictive ability, and that's something that we have to solve for. We have to solve for that alpha value. This is a simplified, or an alternative form of the model where we're predicting a value based on history using the alpha as a weight. And how do we determine the alpha value? Well, we sum the squares of the residuals, and we minimize the sum of squares of the forecast errors or of the residuals. And that gives us our optimal alpha parameter, smoothing parameter for exponential smoothing. There is, when we get into the actual software, the software maximizes the log likelihood function, and that's actually very similar to this sum of squares forecast errors. It's just this is easier to understand than the log likelihood. We also have model selection criteria that use the log likelihood, Akaki's information criteria, AICC, which is corrected for small sample, and Bayesian information criteria. So this is when you have alternative models and you want to select which model. And when we use automatic model selection, it will use one of these three criteria, and AICC is the default setting. So the information criteria rewards goodness of fit, but it also includes a penalty that is an increasing function of the number of estimated parameters. So that's how that works. And so it discourages overfitting, because increasing the number of parameters will automatically improve the goodness of fit. So it's an adjustment for that. Also, we have forecast accuracy metrics, so root mean square error, mean absolute error, mean absolute percent error, and mean absolute scaled error. So the scale is useful because The value of 1, if you have a scaled error less than 1, it means that your forecast is better than that which would be achieved by a naive forecast, which is simply the current value predicts the next value. And so if it's greater than 1, it's worse than naive. If it's less than 1, it's better than naive. So that's a useful, MASE is a useful measure. So they're all useful. We provide all 4 in the reports. The other thing about forecast accuracy is that we have in sample 1 step ahead. So this helps you when you're just in terms of building your model, what your forecast, your within sample forecast error is. But errors that really are useful are the out of sample, where you withhold some data and don't use that in the model, and then you compute your forecast errors. So there's out of sample 1 step ahead and out of sample multi-step or full period forecast. Okay, and we'll be looking at these with some examples. So let me start with a demo of simple exponential smoothing. And this template is available in SigmaXL. It's called Demo of Simple Exponential Smoothing. And what I have is I've set this up using, it's just pure Excel functions, and I have it set up so that I can vary alpha and I can vary the initial level. So if, for example, I vary alpha and I make it 0.99, basically what we have is a naive forecast. The current value predicts the next value. If I have an alpha of 0.01, it's basically almost a smooth line. So there's too much damping going on. So something between 0.01 and 0.99 will be optimal. And the optimal is going to be that value which minimizes the sum of squares error. So to illustrate this, we will use solver. Actually, I'll change that to 0.1 as a starting value, so I have a more reasonable start. And again, this is not something you won't need to be doing this, but I like to just demo this. So what I have is solver will automatically find the values of alpha and initial level that will minimize the sum of square error. So if I run solve, and there's our results. So an alpha of 0.295 and an initial level of 16.7 minimizes our sum of squares error. And that's really what's going on under the hood when you run exponential smoothing in SigmaXL. Only the models get a lot more complicated because you can have trend, you can have damp trend, you can have seasonality, you can have multiplicative or additive seasonality, you can have multiplicative or additive errors. So it handles much more complex models, but it's all the same principle. And you have these model statistics, AIC, ASEC, and so on, and then the in-sample forecast accuracy metrics. These become more useful when you're comparing models. Okay, so that's the demo. And now what we want to do is we want to now take the same data and run it, and we're going to specify the model. By the way, you can do automatic model selection, or you can specify your model. If you specify your model, the error can be additive or multiplicative. You can have no trend, additive damp. And if you have seasonality, you can have additive or multiplicative seasonality. All right, so with that, I'll switch back over and go to the chemical process concentration data. And I will run SigmaXL time series forecasting exponential smoothing forecast. And I will specify concentration as my Y. I'm not going to use the time axis label here because it's just the observation number. I'm going to have 24 forecast periods with a prediction interval of 95%. Here's where we do withhold. I'm not going to do a withhold right now. We'll do that later. If I wanted seasonality, I would put that in here, but I'm not going to do that. If I wanted Box-Cox transformation, I would check that, but I'm not going to do that. So I'll turn on the various plots, diagnostic plots, go to model options, specify model. And so I'm specifying that I want a simple exponential smoothing with additive errors or an EWMA. So that's your basic exponential smoothing model. And then we'll click OK. And it's basically the exact same model that we did by hand here or using solver. So we have 0.295 for alpha, 16.7 for initial, and you can see that the coefficients match what we achieved. Now the difference here is that it does include the forecast and the prediction intervals for that forecast. So that we don't produce on the demonstration sheet. But everything else, all the statistics are the same. You have 197 observations, 195 degrees of freedom. You lose 2 because of the 2 terms in the model. And then you have these statistics, again, as I mentioned, are used when you're comparing models or building models automatically. And forecast accuracy will be more useful when, again, when we're comparing or we're comparing in sample to out of sample. So as you can see, this models the motion in the mean quite nicely, and it gives you a model. You can also look at the ACF plots. This is the before ACF and the after. So this is the ACF autocorrelation on the residuals. So you can see the model has done a very good job of removing the autocorrelation. So there's also partial autocorrelation. That becomes more important when you're doing ARIMA or ARIMA models. Both are useful. In this case, we have removed both the ACF and the PACF. The one thing, there is this what's called Lejeune box. Red means that there is still some significant autocorrelation. This does not mean that it's a bad model. It just means that possibly the model can be improved and that the prediction intervals might not be quite accurate. That is, a 95% prediction interval might not actually be 95%. So this is kind of a useful diagnostic, but it's not a showstopper for a useful model. All right, so that's the simple exponential smoothing. We did the demonstration. This is the formula for the Lejeune box test. I'm not going to get into the details, but as I mentioned, it does not mean that the model is a bad model. It can still be very useful for prediction purposes, but the prediction intervals may not provide accurate coverage. You also have your residuals. So let me go back. Just as you would with any regression analysis, you want normally distributed, no obvious outliers, and that's pretty well what we see here. Roughly a straight line in the normal probability plot. No obvious signals or out of control points. And you can, of course, you can control chart the residuals because the autocorrelation has been removed from the data. And that's effectively what we do in the control chart section. Once we've modeled the data using an exponential smoothing or an ARIMA model, we then control chart the residuals. And we'll deal with that in the next webinar. So the next thing I want to do is I want to take the same data, and now what I want to do is I want to put in a withhold period. So I'm going to rerun the analysis, but I'm going to exclude 24 data points, and I'm also going to do automatic. I'm not going to specify. I'm just going to let it go and let it pick the model itself. So I'll go back, and we'll do the time series forecasting, exponential smoothing, forecast, concentration. This time I will specify 24 withhold periods. And this is non-seasonal data, so I don't need to do that, and there's no need for Box-Cox transformation. This is a one-step ahead prediction error that we're looking at, which means that the model will update with every new data point. Even though those 24 points are withheld, every time a new data point is added, the prediction is updated. If you want to predict without any updating, you would select multi-step ahead. What that would do is that would predict out for 24 periods without any updates. So the easier one is the one step ahead. But it really depends. Are you more interested in short-term forecast or long-term forecast? If you want to know how the model is doing one step ahead, then you use a one step ahead withhold. If you want to use the model for predicting out for a year or two, let's say if you have monthly data, you want to predict out 12 months or 24 months, then you would use the multi-step ahead. In this example, we're going to use the one step ahead. And okay, so you can see now the light dots correspond to the data points that have been excluded from the model. So the model now has fewer data points. The original model had 197, and this is only using 173 data points. It was automatic, and it chose multiplicative errors, so that's a little bit different from what we ran manually. Practically, not much difference, but it just found that the multiplicative gave a slightly better AICC, so that's why it went with that. Notice that if you compare the forecast accuracy in sample to out of sample, the out of sample has slightly higher errors than the in sample, and that's to be expected. Okay, so that's the automatic model selection, forecast accuracy. The parameter estimates really didn't change all that much, even though we removed the 24 data points. So we'll go back to the PowerPoint. And we're ready for our next example. Now we're ready to look at seasonal data. So in this example, what we're going to look at here is, this is the airline passenger data. And so it has strong seasonality. This is monthly data. And the seasonal pattern gets larger over time. So it's seasonality that increases over time, and you have a strong positive trend. So one of the things we would want to do is to take the logarithm of that data, because that logarithm nicely takes out the stationarity in the variance, seasonal variance. Now, we can use Box-Cox transformation to do that as well, and it will basically do the same thing. It will apply a logarithm to the response. The other thing is to mention is that exponential smoothing does have multiplicative capabilities, so you can use Box-Cox or you can use a multiplicative model. You can try either or. In this demonstration, we're just going to go with the Box-Cox and run with that analysis. But keep that in mind, that because you do have a multiplicative seasonality option in the exponential smoothing. In terms of looking at the seasonality, we have what are called seasonal trend decomposition plots. And what that does is that decomposes, so you can actually nicely see the trend and you can nicely see the seasonal. And here is the seasonal component, here's the trend component, and here is the remainder. And these three add up to the data, to the original data. It's an additive model. Now, that's why we wanted to use LON, because we don't have multiplicative decomposition. It's strictly additive decomposition. So when you have a case where it's a multiplicative problem, but you need additive, then just take the logarithm, and that will allow you to use an additive model for decomposition. Another thing we have is a spectral density plot. Here we know, because we have monthly data, and because we have monthly data, we know our frequency is 12, but sometimes you don't necessarily know your frequency, and you run the spectral density plot, and it will tell you what frequency the seasonal frequency is. And it will differentiate between values that are perhaps lower in signal strength versus it will actually do a test to compare signal strength and give you only those that are significant in terms of seasonal frequency. You don't want to have too many frequencies in your model. We can accommodate multiple frequencies. Typically, you only use one, but maybe 1, 2, or 3 frequencies, and the spectral density will give that to you. Again, keep in mind that when we say frequency, this is not the same as Fourier analysis or what you would normally use in an engineering application. Okay, let me just discuss exponential smoothing. Now, we looked at simple exponential smoothing. We can expand that and include trend, and that's known as Holt's linear or double exponential smoothing. And then if you have error, trend, and seasonal, this is known as Holt-Winters or triple exponential smoothing. And when you have that, again, the software will use the AICC and go through the various models and pick the best one. And that's what makes this really easy to use. I'm not going to get into all the details here. Basically, this covers the breakdown. This taxonomy, which we use, is based on Rob Hyndman's work, and there's a free book that he has online, Forecasting Practice and Principles, and it's referenced in the slides at the back. Very useful, free online. Of course, it's based on R, but SigmaXL is capable of doing pretty well everything that's in that book. So we recommend that book. So error can be additive or multiplicative. As I mentioned, an alternative to multiplicative is the Box-Cox transformation. You have a trend. You can have additive trend or additive damped. Multiplicative trend is not included as they tend to produce poor forecasts. And seasonal can be either additive or multiplicative. And here are a bunch of different options that are considered. Again, we're not going to look at all these, but just to point out that there's a whole catalog of exponential smoothing models that are considered in the automatic modeling, or you can manually specify any of these models. If you happen to know that a Holt linear for your application is an appropriate model, then you can specify that. And this is a dialog, as we've already seen, on how you specify your exponential model. AICC is the recommended method for model selection. If a Box-Cox transformation is used, multiplicative models are not considered. So we're going to now run the monthly airline passengers using exponential smoothing. And I'll go ahead now and go to monthly airline passengers and exponential smoothing. So I'm going to go with not the transform, but I am going to go with the monthly. I'll put the date in. I'm going to withhold 24. And let's say I'm interested in long term, so I'm going to switch the multi-step ahead. I want a seasonal frequency of 12. And I'm going to use automatic model selection. If I specified, I can click specify, but I'm not going to do that. I'm going to go with automatic and AICC. And I also want Box-Cox transformation because we know that there is this increasing seasonal variance over time. So we'll include that. As I mentioned, it's not necessary. You can try either or with an exponential smoothing because it does have that multiplicative error and multiplicative seasonality. And so with that, I'll run this model. And we have our exponential smoothing. You can see it very nicely tracks the seasonality. And this, keep in mind, this is a 2-year forecast, so it's quite long term, but it's tracking the data very well. And we have our statistics. It's considerably more complex because of the seasonality. This is an additive trend, additive seasonal with additive errors. So basically, it's a Holt-Winters model. So you have more parameters. You have your initial seasonal values. Really, I wouldn't be too concerned about this, but this is the model that is used. What we're interested in are things like forecast accuracy. And notice that the out-of-sample is quite a bit higher than the in-sample. So that's, again, very useful. But that's to be expected because we're predicting out for 2 years. So we would expect out-of-sample error to be larger than our in-sample error. I also want to mention that because we use Box-Cox, you'll notice this is the raw data. This is not the logarithm, but we are using the lambda of 0, which is the logarithmic transformation. So the data are, we apply the inverse transformation, in this case the exponential, to get back to the original units. We also have our ACF, PACF, and as you can see, we've done quite well. Residuals here, Legendre box, not so good. But as I mentioned, it doesn't necessarily mean that it's a bad model. It's still a useful model. Possible improvements, and the main area that is impacted are the prediction intervals. The residuals look good. Basically, not quite normal, but nothing really standout obvious. So that's the airline passenger data using exponential smoothing. That was automatically selected. It nicely fits the data. And then ARIMA is the Box-Jenkins AutoRegressive model, and that's a different model, and that can include seasonal and non-seasonal components. You can specify, and I'm not going to get into the formulas, but basically you have an autoregressive component and a moving average component, and you can manually specify your ARIMA model, or you can let the software automatically determine the best model in ARIMA. And it will stepwise consider different orders, differencing, and different orders for the moving average term and the autoregressive. And so basically now what I want to do is I want to take the same monthly airline passengers and redo exactly what we did with the exponential smoothing and do it with ARIMA. So I'll go back to the monthly airline passengers, and now I'm going to go to an ARIMA forecast. And again, monthly airline passengers, we'll put date. We're going to withhold 24. We're going to do exactly what we did before with exponential smoothing. We want to specify 12. And I want to do a Box-Cox transformation. So we can run that. Then we can compare between the exponential smoothing and the ARIMA. Both are seasonal models. And again, visually it looks pretty good, although it does appear that there's some bias on the prediction here. And then if you look at the errors, you can see, in fact, that the errors for the exponential smooth were lower than those for the ARIMA. So this is an example where exponential smoothing actually did a better job for the long-term forecast. Now, keep in mind that if I had predicted for 12 months, ARIMA might have done a better job. So both are useful. Try both and see which one gives you a better forecast accuracy, and go ahead and use that, or take the average of the two. So the last thing I want to talk about are ARIMA with predictors. Basically, that's just a regression model that includes predictors. Okay, so if you're wanting to make a prediction, one of the things you have to do is you have to add additional data points for the X's. And the example that we're going to use is electricity demand. And we will include temperature and workday. And so we need to add, if we want to predict for 2 weeks, then we have to put 2 weeks worth of temperature and workday values in the model. Okay, so all the same rules apply for regular regression. You don't want to have predictors that are correlated, so you want, or not necessarily orthogonal, but you want independent predictors. You can't be putting things in like a column of all the same values, or anything that's going to crash multiple regression will crash the ARIMA model as well. So we're going to look at this electricity demand, This is actually data, daily electricity demand with predictors, again from Hyndman's book, FPP2. And you can see this is Australian data. So basically, the demand, this is demand versus temperature. So you can see when the temperature is high, the demand is high. When the temperature is low, the demand is high. So you have very much a summer-winter effect. And if you look at demand versus temperature, you can see a nice quadratic curve. And so that's why in the model, we're going to include the both temperature and temperature squared. So that's what we'll do now. We'll go ahead and we'll build our model using the daily electricity demand. So we have the demand, we have the temperature that was recorded, temperature squared, which is just a calculation, and then workday, 0 denotes a weekend or a stat holiday, and then as well at the bottom, we include the 14. So you can see here, we have a year's worth of data, and now we want to predict into 2 weeks into the new year. And so we would use our weather forecast, or in this case, we're just going to use a best estimate, a single point value. You can do that. But the workday, we already know in advance what the workdays are. So we put that into the model. If you have a weather forecast, you can actually just plug those numbers in and then include those as predictors. So we'll go ahead and we'll do a ARIMA forecast with predictors. So I'm doing demand as my Y, electricity demand, date, temperature, and temperature squared are continuous predictors. Workday is a categorical predictor. I'm not going to do any withholds, not going to do any seasonality, not going to do Box-Cox. And I'll go ahead and I'll run that. This one takes a little bit longer because it's a very demanding model. Electricity demand, it's a demanding model. And it's going through and it's crunching through, and it's ARIMA, and ARIMA has more possible models than exponential smoothing does. But unfortunately, with exponential smoothing, you can't include predictors. Okay, here we go. So the red line is our prediction, our forecast. And here's our 14-day prediction, the new year, basically the electricity demand that we forecast for the first 2 weeks of January. We didn't do a withhold, so we don't have any out of sample. We could do that, but I'm not going to go back and redo it. But I just point out we do have our forecast accuracy statistics. Notice the model does some differencing, but we did not include seasonality. Let me redo this, because what I really wanted to do, I want to put in a daily seasonality. So now the model is a little more complicated, and we'll rerun that with a frequency of 7. So I have, again, seasonal frequency. With the drop-down, you can say quarterly, daily, monthly, hourly, weekly, or you can automatically detect. And if you automatically detect, then that kicks in with the spectral density analysis. And you can do that, of course, separately as a utility. So let's go ahead and run this. So the first one we did was non-seasonal. Now I'm doing a seasonal model. So it's going to be a little more complicated. We can then compare the errors and see how the two models did. Again, this takes a bit of time. It's probably about a minute. It has more work to do because we're adding seasonal terms as well as non-seasonal terms. And it's going through the moving average, AutoRegressive, non-seasonal, moving average, AutoRegressive, seasonal, and doing stepwise. So here we go. Let's see, how do we do? So it's a different model, of course, because now we do have a seasonal frequency of 7. So we have AutoRegressive 2. It's actually simplified the model somewhat. We had an MA4. Now we have a AR2 and an MA2. So it has reduced the order of the term. Again, you have your temperature, your temperature squared, your workday as part of the model. And here I have an RMSE of 6.6 versus 7.3. So the model has, by adding the seasonality, we did get better. MASE 0.33 versus 0.35. So yes, it's a bit of an improvement. And that's the sort of thing you want to do. You want to experiment. You want to look at your forecast accuracy. And that concludes my presentation. So I'm now going to open it up to questions. Let's just see what we have here. What is the limit on observations used for forecasting? Can you have too much data or too granular data by the hour? You have to roll it to monthly. Excel permits 1 million rows, so you can do that, but you have to ask yourself the question, if you have that much data, in all likelihood, it's probably not going to be all that useful for predictive purposes. So you're better off using more recent relevant data. In other words, look, let's say you're doing something where you're interested in month. Well, then you need to go back maybe 10 years if you have it, if you have access to 10 years worth of data or 5 years worth of data. So it depends on what it is you're interested in. And on the other hand, if you're looking at data by the minute, then you're going to have a lot of data very quickly. So SigmaXL can accommodate that, but the model building is going to take time, and you're basically limited by memory and by Excel. And I just generally don't, like if you're going beyond 10,000, you can do it, but you have to ask yourself practically, the goal is to build a good predictive model, not necessarily use everything you have. And if you have, thousands and thousands of data points, it's not necessarily the best thing to use all the data. So I hope that helps on the question, what is the limit on observations used for forecasting? Can you have too much data or too granular data? And so, yes, I would say you can have too much data. Any other questions? We'll wait for a little bit. I know we covered a lot of territory, so just remember, everything I've covered is in the workbook, so you can go through and review that. Having seen the webinar, you can go through on your own and repeat the steps that I've done here. This video will be available in a couple of weeks. The PowerPoint slides are available. The data sets are available under sample data. We, of course, also have the aspects of the tools, time series forecasting, that I didn't cover are included, such as the utilities. We have a missing value utility that may be useful. I didn't mention missing values, that the ARIMA can accommodate missing values, whereas the exponential smoothing does interpolation. So just to mention that. Now let me just mention the references. I have my references listed here. Some of these references apply to the presentation I'm doing in December for SPC for autocorrelated data. In December, it will be control charts for autocorrelated data, Thursday, December the 10th. So we look forward to seeing you then, and I hope that this has been useful for you. So thank you all very much for participating in today's webinar.